Chapter 3 deals with exponential functions and logarithmic functions. So today first lecture will deal with some exponentials and their graphs and a few properties. So remember, an exponential graph is this form here, where you'll notice that the variable x is now in the exponent position, and so you have a base raised to a number that's going to be changing all the time. So it's not the same as, when we had x squared, that was fixed. The exponent was fixed. Now you have this, and so this is changing now. So let's go ahead and take a look at a graph. We can use a basic table to help us do this. I'm going to start with 0. Remember that anything to the 0 power, that's going to be a 1. And 2 to the first is 2. And 2 squared is 4. And then I can just write it like that. 3 squared. Oops. 2 is my base, and 3 is the power. Sorry. So that'll be an 8. So the variable is changing. The exponent is changing every time. Now remember, when we do negative exponents, so let's do 2 to the negative 1, what you're going to do is flip your base into its reciprocal. So the reciprocal of 2 will become 1/2, and that allows you to change the exponent to a positive number. So now you have 1/2. And if I do the same thing with the 2 to the negative 2, I flip my base again. Now I have the positive exponent, and that will give me 1/4. And then you can start to see the pattern, and this will be 1/8. And you can go to your graphing calculator and type in 2 to the x and see what it looks like. But now if I go and graph it, 0, 1 is the y-intercept. And so on this side of the graph, my green numbers, right, it was doing something like this. It goes up and to the right, and it's growing at a very quick rate. And then the numbers back here are coming down, and it's going to follow the x-axis. So there's this imaginary line right here. And it's because every time you flip the base into its reciprocal, you end up with a 1 on top. And even if you take 1 divided by a really large number, it will never equal 0. So that's called the horizontal asymptote. So now we're going to flip over and look at our calculator. We're supposed to do 4 to the x. So we're going to do 4 to the x on the calculator. So go to your y equals, and we can clear this out. And a base of 4 raised to the x power. And so you'll notice it hits 0, 1 as the intercept again. So all basic exponential graphs have a y-intercept of 0, 1. They will go up and to the right at a quick rate, and it'll go against the x-axis here very quickly. Now these are not really touching. So if I go into the window here and maybe just go from 0 to 1, that's even tough to see there. But it goes against the x-axis so quickly that you can't really tell the difference, but it does not touch. So back to Zoom 6. So they ask us, do you notice any similarities of the graph? So now if I go back to the calculator and I go to y equals, and let's put in our other graph, 2 raised to the x. So the bases, it looks exactly the same. But what you can see right here is they both hit 0, 1, but the blue graph, because it has a larger base of 4, it's going to go and get closer to the x-axis quicker than the red one, which has the smaller base. And then on this side, the blue one grows at a slightly quicker rate, so it's going to look like it's going up the graph faster than the red one, which was just 2 to the x. So if you ever graph them on the same one, you can see that. All right, so the next one is this DIY. So go ahead and make a table. Be careful when you plug in the exponent, and let's see what you come up with. So pause the video now, do the graph, and then come back and look. So you can see we're doing 2 to the negative x, and the graph is a reflection over the y-axis. 2 to the 0 is still 1. But now when you put the 1 in, and the 2 in, and the 3 in, it goes in as a negative exponent, which flips it. So the 1, 2, and 3 are the flips, and so that's why it's getting closer to the horizontal asymptote. And the negative, when you put it in, is really ending up plus 1, plus 2, plus 3 as the exponents, and you're seeing the growth, quick growth on the left-hand side. Now you're going to look at example 4, another DIY. So go ahead and use your calculator. You can type that in, but I bet if you drew it right now, you would know it. But go ahead and do that now. So pause the video and come back and look at the answer. So after the DIY, you can look here. It's going to be very similar to 2 to the negative x. And basically this little sketch right here is good enough. But just know it's just like the other one. The larger the base, the faster it will go against the x-axis. The larger the base shows more growth, so it actually would be closer to the y-axis here. There's an example 3.1. Example number 4 and 3.1 would look something like this. So in your textbook, if you want to go to the online textbook and just kind of read through this example and look at these pictures, I would do that now. So this one is answering the question, what's wrong with this diagram? So I'm going to give you a moment to kind of read through the question that's asking you, and then go ahead and describe anything that you noticed here, and I will put the answers up. So pause now, kind of read through this. Okay, so if we look at what's wrong with this diagram thing, you can see that they wanted you to do 3 to the x and 3 to the x plus 2, and they moved 3 to the x plus 2 up 2, but that plus 2 is actually inside the function, and so it's going to be a shift to the left 2. And you could graph that on your graphing calculator to see what we're talking about. And then they asked you to look at these two graphs and see what's going on, what's the difference between them. And so if you graph them, you would notice that the negative 2 would be a flip top to bottom, so over the x-axis, and the negative x in the exponent would be a reflection over the y-axis. It's going to flip it side to side. And again, you could graph those two, do 2 to the x, and then graph the various ones that you're seeing. Now we're doing natural base E. So E is a symbol that we use in math. Similar to like pi, it has its own symbol. So we're going to take a look at what this number is, and we're going to try to find an approximation for E. So use your graphing calculator, graph 2 to the x, e to the x, and 3 to the x, and use the graphs to make an approximation. Okay, so you can see the two graphs. The blue one is 2 to the x, and the red one is 3 to the x. You can also tell because the red one has a steeper growth rate than the blue one. So what they're saying is if I put e to the x in my graph here, so I hit second ln, notice right above the ln button is that e to the x. So it's what it means. You can put e to whatever power. So I'm going to put an x in for that. And now when I graph it, what does that tell you? Well, it's between 2 and 3, but it obviously it's closer to 3 than it is the 2 because it follows it so close. So on our graph over here, we could just type in, another way to get e is to do second divide. You can hit enter, or you can hit second ln and raise it to the first power. But you'll notice that it's a crazy irrational decimal. It just goes on forever. That's why it gets its own symbol like pi. So going back to the graphs, we're supposed to ask the questions, are the exponential graphs functions? Yes, they pass the vertical line test. Are they one-to-one? Yes, they would pass the horizontal line test. And what does it mean if it passes both the vertical line test and the horizontal line test? So what does it mean if it passes both? Remember, it'll have an inverse. So exponential functions will have an inverse function is what that's telling us. Okay, so we can do some applications here. We have done investing money before in Algebra 2. So remember, P will be the principal. So you got to know this formula. P will be the principal, which is the initial amount deposited or borrowed. Interest rate is the R. You need to put it in as a decimal. Always as a decimal. R, right there. N will be the number of times things are happening per year. So the compounding number, how many times is it compounded in 1 year? That's what you put in for N. The formula will take care of the rest. Compounding per year, N. And then A obviously is the amount that you'll have at the end. Another formula is what's called continuous. Okay, so continuous compounding. It gets rid of a part of the graph up here and replaces it with E, and there's a whole formula that you can go through, but if you basically take this part of the formula and let N get bigger and bigger and bigger, it starts to reach a number that looks like E, the 2.71828 thing. So let's look at a couple examples and see what's happening. If $3,000 is invested 6% compounded, okay, so if the money is invested 3,000 at 6% compounded daily, what's going on? So I can use my A equals 3,000, 1 plus the 0.06. So remember, you always divide by 100. That'll give me 0.06. Daily, we would say there are 365 days in a year. 365 days. Raised to the N, again, 365 for 10 years. Now, when we go to the calculator, if you have a calculator that when you hit the raise to button, it puts the caret there, just get in the habit of putting parentheses times the two numbers there. So when I go to the calculator, clear that out so you're watching. So it's 3,000, and you can put a parentheses in, and you can say 1 plus 0.06 divide by the 365, and we close that, and now I'm going to raise it. My calculator goes into the exponent position, so I can just type in 365 times 10. And when I hit enter, it's money. So let's go ahead and round it properly. So that would be 5,466 So now you're going to look at the next example, write all your formulas out, get all the answers, and then come back and check. So pause the video now. So again, this is DIY. You're gonna do these problems quickly. So pause it and come back and look at the answers. So check your formulas. 8.25% is 0.0825 there. Quarterly, your N is 4. Monthly, your N is 12. So check these two formulas. It's going for 26 years. And then just remember, continuously type in 25,000. If you hit second, LN, so on your calculator, if you hit second, LN, it puts the E on your calculator and it raises it to the power. Also, those of you that have the calculator with the caret symbol, it'll put the E, it puts the caret symbol, and it gives you the parentheses, so you don't even have to worry about that. So that's kind of nice. So second LN. But make sure these are your answers and that you're rounding to 2 decimal places because we're talking about money. All right, last couple of examples. City's population is growing at a rate of 8%. After T years, the population is given by this formula. We use E for population growth because it's continuous growth. So if I want the initial population, I'm going to put 0 in for T. So when you do that, 0.08 times the 0 is 0. E raised to 0 is 1. And so when you do all that, you'll get 450,000. That is the initial population, the starting point. Now put 20 in. So let's just go ahead and do that on the calculator. We're going to put 20 into our formula. So I have 450,000. And then I can go second ln 0.08 times 20. And you see we have a population of about 2,228,864 people. If you want to round that up to 265, because the 5,9 would tell, the 5 tells us to round up. So what is the initial amount here? Again, if you put 0 in for T, you end up with 16 to the 1/2, 0 over the 1600. So that's 16 1/2 raised to the 0 power, which again would be 1, and we're left with 16 grams. So the initial or starting amount is that. And now if you plug this in, you do 16 and put 1,000 years over 1,600 years. So pretty easy to go to the calculator. So 16 and now we want to raise that to the 1,000 divided by 1,600. And so there'd be about 10.37 grams left.